as with section 5.2, we're going to put together everything we've learned. This is actually the exact same example as in section 5.2, so you can consider it kind of an extension of that same example, but we're going to be going over the things that we learned in section 5.3 in this bit. Okay, so hospital records indicate that random kidney transplant patients stayed in the hospital for the number of days shown in the distribution over the past 5 years. Why is it safe to assume that these patients are independent of each other? Okay, so we talked about in the previous video, actually the previous section, why they're disjoint. A patient cannot stay 4 days and 6 days at the same time, right? So that's why they're disjoint. Now they're independent because if a patient stays 4 days, that has no impact on an unrelated patient staying 7 days and vice versa. So let me write that down. All right, I kind of wrote both of them up, so that way you have a reference for both of them, because these kind of questions get asked. So they're disjoint, right? The days stayed are disjoint. I said events, but I could say days stayed. So the days stayed are disjoint because a patient cannot stay both 4 and 7 days, or 3 and 5 days, or whatever. I just kind of made it up. So days stayed are disjoint because, right? And they're independent because if the patients are random, which we assume they are, then one patient staying, I just made it up, 5 days, right? It has no effect on the number of days the next patient stays for, right? Or one patient staying 7 days has no effect on the next patient, and so on. Again, it doesn't have to be 5, I just made it up. Okay, so you're going to select 2 patients at random. Now, since these are random patients, this is going to be a multiplication rule. They're independent. We just said up above they're independent. They're actually disjoint and independent. But disjoint doesn't really affect us here because disjoint would only be for if we were going to talk about a single patient, which we're not. Okay, so since we're looking at 2 patients, then we're going to use, and we want the probability that both of them stayed for 4 days. Well, remember, both is a hidden and. It really means the multiplication rule, right? From the previous, or a couple pages ago, I should say. So this is going to be multiplication rule. It's rule number 4. All right, so the probability of both patients staying 4 days is the probability that the first patient stays 4 days, right? That's the first patient, times the probability that the second patient stays 4 days, which is the probability of 4 times the probability of 4. I should say the capital P is standing for the word probability. So once you put the numbers in, you don't write capital P anymore. Capital P means probability of, right? So once you say 0.252, that is the probability. So you never write P of 252. You just say 0.252 to the 2 power, right? Or 0.252. I hit the A to the B button and 2, right? So 0.0635. And there you have it. Notice there's no capital P's there, right? I don't technically even need the parentheses there. I just put it there because I think it makes it cleaner writing-wise. All right, now we're going to select 3 patients at random. What's the probability the first one stayed 7 days, the second one stayed 3 days, and the third one stayed 5 days? Well, these are all independent, right? So again, this is rule number 4. It's just that there's more of them. So I need the probability that the first one stayed 7 days times the probability that the second one stayed 3 days times the probability that the third one stayed 5 days. All right, so 7 is 0.039 times the second person staying 3 days is 0.118, and the third one staying 5 days is 0.4 4, 4, 1. First person, second person, third person, and you multiply them because whenever you're dealing with more than one, we multiply. Remember, whenever there's multiple events, you multiply. Right? Multiple events happening at once, I should say, which this is. There's an order. There's a sequence. And so when there's an order or a sequence, use the multiplication rule. And there you have it, 0.0020. And the last 0 doesn't have to be written, but there it is. All right, now we're going to select 4 patients at random. All right, so I know this is going to involve the multiplication rule at some point, but it has this magical phrase of at least one. Right, so at least one in multiple trials, that's rule number 5. Rule number 5 only works for multiple trials, I should say. You can do at least one when you're only selecting one, but that's a different story. Like, for example, I could do at least 6 on this, right? But that works differently. So it's important that you know that it's multiple trials. It has to be out of 4 patients or something like that. All right. So I'm going to have to figure this out. So the probability of at least 1, and they want 3 days, right? At least 1 3-day is 1 minus, and you put the probability of not 3 to the n power, but n is 4 right here, right? So I'm going to go to the 4 power right here. All right, well, I'm going to have to go off to the side, remember, and figure this out for a 1 trial, for 1 patient. All right, for a single patient, the probability of 3 is given to us in the table. It's 0.118. So the probability of not 3 is 1 minus 0.118, which would be 0.882. I can prove it. 1 minus 0.118. There you go, 0.882. So that's the value that gets placed into the rule. So then we say 1 takeaway, so a second 1 minus. So we have 1 minus here, but for a single patient. Then I have another 1 minus for the rule. And then that 0.882 goes in here. And I'm just going to type that in Desmos as it is. So that's what Desmos is for. So 1 minus 0.882 to the 4th power. And if you want parentheses around it, you can do that. 0.3948. It's super important that you don't skip this step. A lot of students try. A lot of students try to do this all in their head, and they end up with the wrong value in here. Take the time to write it out. Probability of 3, probability of not 3. This is all for a singleton. Then go plug that singleton probability into this rule with the 4th power, and it will take care of it. Trying to skip steps is a very dangerous step, dangerous idea in this particular section.